Hello, welcome. This lecture we will talk about how to understand the topology in real materials, like how to identify a topological insulator, which material is a wire sand metal. And before go to the materials, let's go to the tool. How do we calculate a material? And the most well-known tool is this density functional theory. Here is this Dft method. And in a general many body question, in the solid, most of the material we study, there are many electrons, like more than millions or billions of electrons and atoms. And this is the typical many electron problem or many body problem. And then for a typical way, how do we solve it? Well, we can always write the Schrödinger equation. And this is the many body wave function. And for each electron, its position is represented by R. And then for n electron, number n electron, we will have 3n degree of dimensions. For example, if we have a very simple benzene molecular, and we will have 42 electrons. And in total, we have more than 100 degree of freedoms. This will be, in practice, very hard to solve. There's another way to solve this problem. Actually, we can not think every individual electron. Actually, we just use the total charge density of all the electrons. Actually, the total charge density rho. And then this total charge density is only a function of x, y, z. There are only 3 degrees of freedom. And actually, this practical way is the heart of the Dft theory. Let's go to the Dft theory. Actually, the Dft theory was developed in 60s. And there are 2 very important assumptions. The first one is the system, especially the Hamiltonian, the wave function, and the total energy can be written as a function of the total charge density. Then the second one, how to calculate the charge density, is just to minimize the total energy, find the ground state. As long as we reach the ground state, we observe the correct charge density, the ground state charge density. When we have the charge density, then we can get the Hamiltonian, then we can solve the system, right, for a real material. Here, this term is the energy functional. The first term is the Hohenberg-Cohen function. And the second term, just the external potential generated from the atoms. This density functional theory provides actually a practical way, a very ideal way to solve this many body problem. And actually, this method was celebrated by a Nobel Prize in 1998. And okay, this is in theory, this will work. However, we miss something. Nothing is perfect. This functional, Hohenberg functional, this part, we still don't know the exact form. This Dft theory first part only prove, okay, this is possible. In math, it's accurate. We can solve this problem in this way. However, it does not provide how this functional exactly looks like. Technically, how do we do it? Then this comes to the next step. This is called Kohn-Sham equation. Here in the Kohn-Sham equation, actually, this is the total energy is written in this way. The exchange correlation interaction between electrons are approximated as this local density approximation. In practice, actually, this exchange correlation potential term is approximated by a free electron gas. And in this way, this Kohn-Sham equation reduces this many electron problem to a single electron question. That's to mimic the interaction between this electron with all others as an effective potential. This potential just becomes a background. We can solve it exactly. And this approximation. The power of this approximation is it reduces this many body problem to a single particle problem. We can diagonalize the Hamiltonian and solve this problem exactly. It has a price. The price is this approximation. This approximation approximates everything, the interaction, as a uniform electron gas. Therefore, it means it can treat a metal fairly accurate because metal is close to the uniform gas. And for a small gap insulator, it works. However, for other systems with much strong interaction, for example, strongly correlated materials, and it will not work. But fortunately, this topological material, most of them we study today, are either metal, like the wire sand metal, Dirac sand metal, or small gap insulators, like the topological insulator and the topological crystalline insulators. That we will see later. Today, the Dft theory actually is well developed. There are many available program packages for you to calculate materials. And as a beginner, where to start? And what you only need to tell the program is the structure of the system you are interested in. And the structure means the atomic position. It's which element. Yeah. With that, the program already built up. To build up the Hamiltonian, like a kinetic part is standard, the Hartree potential, as long as you know how many electrons, the total density. The external potential is the atomic position, and the exchange correlation. The exchange correlation is this Kohn-Sham approximation one. As long as you know it, you input this information. Actually, mainly is the structure. The other part is the DFT program already built up for you. What output you have? Then you can get, let's see, you can build up the Hamiltonian. Then the Hamiltonian, you get the diagonal Hamiltonian, you get a band structure. Not only band structure, you also have this block wave function. And the wave function in the real space distribution, also the symmetry of the wave function, for example, the parity here. You can also simulate a surface state. And we will talk about how to do it later. You get a surface band structure. You can even calculate the surface density of state that to simulate a STM image. Now let's go to an example. And this is the typical example of silicon. Silicon is the most well-known semiconductor. And well, this is the real material silicon. However, we know in theory or in the atomic structure, there are many, many silicon atoms. And it's infinite in 3D, but it's periodic. We know this is the unit cell. As long as we get a unit cell with the periodic boundary condition, we get the full information of the material, right? Therefore, what we only need is identify the unit cell, identify the atomic position in the unit cell. Then we plug it into the Dft theory. From Dft calculation, we can get a band structure, for example. And you see this is a typical band structure separated by the band gap, their valence conduction band. This is a typical band structure of a semiconductor. By the way, this band gap is slightly smaller than the experiment one. The reason is this local density approximation. Now let's go to another more complex example, how to simulate a surface. And then what is a surface? This is the first question we ask. How is it different from a bulk? This is a three-dimensional bulk. Let's open this material, or in experiment we call it cleave. Cleave the material, we create a surface. Then what is surface? The surface, if an electron live on the surface, it will see one side is vacuum, the other side is the bulk material. The bulk is half infinite. And this is a surface. But how do we simulate? To compromise with the periodic boundary condition, we usually use a slab model. Slab means we have a thick layer, it's periodic in the xy plane, but along z-axis, there's some vacuum to separate the neighboring slabs. And then we have a top surface, we have a bottom surface, right? We have two surfaces. And if we calculate this slab model, its band structure, we will get the information of surface states. For example, here, now we just plug in this slab model into the Dft theory. What we get? We will have a band structure. But we ask a natural question, where is the surface states? How the surface electron behave? And we know we not only get the band structure, we also have the wave function. Check the wave function for every band. We know this wave function live on the surface, either the top surface or bottom surface, or live in the bulk. If you live on the surface, it's the surface states. And if in the bulk, that is the bulk states. Actually here, this is the typical surface state for a topological insulator, and the red curve is the surface state. You see a beautiful Dirac cone there. Later, we will go to more details. Okay, for a summary here, we have this density functional theory. It's reduced this many electron problem to a single particle one. With this approximation, although it sounds very rough, actually it's super powerful to understand most of the materials. Today, this is already a very popular method to calculate the materials. And next, we will use this Dft theory. We use this technique to understand the band structure. From the band structure, we can extract the topology and all the other information. Okay, see you in the next sessions.